according to a research effort led by the US Department of Energy's National Renewable Energy Laboratory (NREL), the use of thermochromic windows in office buildings improves energy efficiency across all climate zones in the United States by modulating the temperature inside, leading to a massive savings. The thermochromic windows, based on the use of perovskite materials to absorb energy from the sun, shift from transparent to a visibly absorbing or reflecting state. The technology mitigates heating loads in warm climates and cooling loads in colder regions. Lance Wheeler, principal investigator on the project, said switching to thermochromic windows saves a significant amount of energy annually, with the main source of savings coming from recovering less heating energy for highly glazed office buildings in cold or seasonal climates. The findings are detailed in the paper Thermochromic Halide Perovskite Windows with Ideal Transition Temperatures, which appears in the journal Advanced Energy Materials. The research, which relied on modeling software Wheeler helped develop called a PV window, suggests adding a thermochromic laminate onto a single pane or even double pane window will yield significant savings. Buildings account for about 40% of all primary energy consumption in the United States, with heating making up the largest contributor. Coating technology revolutionized window energy efficiency beginning in the 1980s by selectively absorbing or reflecting infrared light, but allowing light in the visible portion of the solar spectrum to pass through the glass. However, slightly more than half of the sun's energy occurs in the visible wavelengths, so more energy is required to heat or cool buildings with significant glass facades. The researchers used as their model building a 12-story structure with a window-to-wall ratio of 95%. They simulated energy use in the building in 15-minute intervals for a year in 8 climate zones across the country, covering Hawaii, Arizona, California, Colorado, New York, Wisconsin, Minnesota, and Alaska. They determined that the thermochromic double-pane windows improved building energy efficiency over double-pane windows in each zone, and energy savings were greater in colder regions. Thermochromic double-pane windows outperformed even triple-pane windows in the hottest climate zones. The researchers noted that in colder climates, triple-pane windows provided more energy savings than thermochromic double-pane windows, but adding a thermochromic laminate to create a triple-pane window provided the most annual energy savings compared to the highest efficiency double-pane windows. The thermochromic windows are triggered by temperature, and the researchers calculated the ideal transition temperature falls in the range of 20 to 27.5 degrees Celsius. The researchers coupled the modeling with experimental work and demonstrated a perovskite film sandwiched between 2 layers of glass. The thermochromic switching was proved durable for 200 cycles.